we'll go ahead and begin. We're going to practice solving NMR structures today. And before we do that, let me just mention a couple of housekeeping items. Practice exam 4 is now posted along with the key to it. Let's see what else. Study guides for chapters 13 and 14 aren't due until the practice exam is due, which will be after the final closes. Speaking of the final, it's available on August. That would be fun, wouldn't it? Whew! What a relief. It's available on April 16th and 17th. Those are the 2 days that each of the 2 sections would have been assigned to noon versus 1 o'clock. If we were doing an in-class final, which we're not, it will be delivered over Learning Suite. Both classes will have any time between the 16th and the 17th to take the final. It will be timed, so the 3-hour limit will be just fine. I think it will have maybe 25 to 30 questions, depending on when I get tired of writing it. Pray I get tired quickly, I suppose. Let's see, and people have asked what percentage will be, whoops, rattle. What percentage of the final, and I need to share my screen with these folks, don't I? I forgot to do that. What percentage of the final will be material that we have covered previously versus the newer stuff? And my answer to that is a number that is between 10 and 75. Is that specific enough for you? I don't know, actually. So, yeah, 25 to 30 questions. Trent is pushing for 15 questions. That'd be nice. Let's see, what else? Same rules as before, open book, open notes. You can watch YouTube lectures if you think that would be helpful to you. I don't know why you want to hear my voice any more than you have to. Just don't get help or consult other living humans. You can consult living animals if you want, but not humans. Plants as well, rocks, I don't care. But yeah, you should not discuss the exam with somebody while the exam is open. You shouldn't compare notes with somebody to see if you both got the same answers before you press submit. Just be good, honest people. Other than that, I don't think there's anything else. Yes, there's still a time limit. If you have formal accommodations, I will build those in automatically. If you've seen me for other particular situations or issues and you've already emailed me, I should be able to handle that. If you haven't, go ahead and make sure I have an email from you before the exam. I understand there's some BYU events scheduled during those times, and so I'm happy to accommodate all of those issues. All right. So what we've got so far from NMR is first chemical shift, which, please.
Is practice exam 4 just covering the stuff that we've learned previously and not anything that's coming?
Yeah, practice exam 4 is just for the most recent stuff. So to review for the whole semester, go back to your previous practice exams. You should be able to see all of your previous exams, items missed, responses, correct answers, and so on. All right. Chemical shift tells you something about how many different kinds of protons you have in a molecule and what their environments might be like. This is the shielded versus de-shielded stuff. There is a table and a figure in your text that shows you what chemical shift regions are characteristic of certain functional groups. You should familiarize yourself with that. You can print it out, you can have it open, you can consult it, that's just fine. We talked last time about peak splitting, which tells you what protons are adjacent to. So the key patterns to recognize are a doublet with a 1-to-1 ratio. That says that your proton is next to, or adjacent to, or beta to 1 proton. If you see a triplet and it's 1-to-1, that's 1 to 2 to 1, That's consistent with being next to 2 protons. Of course, the triplet has a cousin called the doublet of doublets, and this arises when when a set of protons is next to 2 non-identical proton. What am I writing there? 2 non-identical protons. The pattern in a doublet of doublets is a 1 to 1 to 1 to 1 4-line pattern. The classic example of this was on a monosubstituted olefin. If we consider proton A versus B and C, the coupling constant between A and B is 10 hertz, whereas the coupling constant between A and C is 15 hertz. And so the pattern you see in that case is a 4-line pattern where this distance is 10 hertz and this distance is 15 hertz. And that pattern arises from, if we could take just the signal for proton A and turn off all of the other coupling, you could split that signal. Let's turn on the coupling between A and C. We could turn on the coupling between A and B first. It may be just easier conceptually to start with the largest splitting. That's the 15 hertz difference. So we split that signal for A into a doublet. And here's where the of doublets comes in, because when we turn on the splitting between A and B, which is 10 hertz, each of these doublets is itself going to be split into another doublet separated by 10 hertz. We would get exactly the same answer if we had turned on the 10 hertz coupling first and then the 15 hertz coupling. You get this kind of pattern because the coupling between A and C is not equal to the coupling between A and B. Of course, if it were identical, let's do a situation where the coupling constants with the neighboring protons are identical to each other. And we look at the signal for proton A. Let's say that the coupling between A and C equals 7 hertz, which is the same as the coupling between A and B. So we split A into a doublet where this distance is 7 hertz. That's coupling between A and C, and then we turn on the coupling between A and B. Each of those peaks is itself going to be split into a 7 hertz doublet, but the peaks in the middle are going to overlap completely, and therefore you're going to observe a 1 to 2 to 1 triplet. So the doublet of doublets is just a spaced out triplet where the central peaks don't overlap anymore. Both of those patterns are useful and important to be aware of. The final one to sort of be really familiar with is the quartet, and this has a intensity or peak area pattern of 1 to 3 to 3 to 1, and this means you're next to 3 protons, most likely a methyl group. I guess we should have pointed out that singlet is the simplest one. That's just 1 peak, and that means you're next to 0 protons. Now, there are other peaks you can observe. Imagine that you have a proton that's adjacent to two methyl groups instead of just 1. That's 6 adjacent protons. That's a septet or 7-line pattern, which you could consult Pascal's triangle to figure out the pattern of intensities and ratio between the peaks. When you get to some of these higher types of patterns, the lines on the outside get pretty small, and it gets increasingly difficult to distinguish one pattern from the other. Yeah?
We're looking at that group with the 2 methyl groups and then the 1 hydrogen. What hydrogen is use NMR.
So we would be observing, I'm sorry, which one did you want to look at?
Well, I guess the quartet, and then like that bottom one.
Okay,
Is that the quartet?
no, that's not the quartet. That was, I should have drawn the quartet example. This is where the quartet comes from. All right. So there are other more line patterns, but this is sort of what you should be most familiar with. The most common way to have two protons adjacent to each other is to be next to a CH2 group. The most common way to have three protons adjacent is to be next to a methyl group. All right? And so these kinds of, being familiar with these kinds of patterns is useful. Now, before we solve spectra, I need to give you one more piece of information about molecular formula and mass spec data. In the study guide for chapter 13, I inadvertently had you do some problems in the text that were related to, given a molecular weight, can you identify a formula that works? It's just sort of math and trial and error, and it's not that useful because nobody does that anymore. What we use mass spec for most of the time now is we make a molecule, we think we know what it is, we predict what its weight should be, we go down to the mass spectrometer, run the sample, and we confirm is it the correct mass or not. If it's not, we did something wrong. If it is, we need to check and make sure it has the right connectivity. So you're not going to be guessing the molecular formula from a given molecular weight. Now, if you have the molecular formula, though, there is information you can extract from it that will tell you something about how many pi bonds or rings a molecule must have. So let me show you saturated hydrocarbon. This is hexane, C6H14. And here is cyclohexane, which is C6H12. And this is one of the hexene molecules, 1-hexene, which is also C6H12. Now notice that the linear hydrocarbon has a formula that fits the pattern CnH2n plus 2. That's the general formula for a linear hydrocarbon, a fully saturated hydrocarbon, one with no double bonds or rings. You may have learned that in general chemistry. Notice that when we introduce a ring relative to the compound that's linear, we lose 2 protons. So 2 protons being missing relative to what you'd expect for a saturated hydrocarbon could be consistent with a ring being present. Similarly with a double bond. Every double bond you introduce accounts for 2 missing protons relative to the formula for a saturated hydrocarbon. So your text uses the term in chapter 10, and we didn't talk about it much there, degrees of unsaturation, which is fine. I prefer double bond equivalents, just because that's what Dr. Savage taught me way back in 2001. I'll abbreviate this as DBE, but what this really means is number of pi bonds or rings. I don't like degrees of unsaturation because it suggests that it's just pi bonds, but pi bonds or rings. And for a hydrocarbon, we can calculate that in this way. 2 times the number of carbons plus 2. That will give us the number of hydrogens expected in a saturated hydrocarbon. Then we're going to subtract the number of protons we actually have and divide by 2, because each ring or pi bond accounts for 2 missing protons. All right, so we would see if we ran the numbers, there is 1 double bond equivalent for cyclohexane, and there is 1 double bond equivalent for hexene. right. Question so far? This is useful because in most NMR problems, you're going to be told what the molecular formula is, and it's useful to know from the beginning how many pi bonds or rings you're going to have to deal with. It narrows the range of possibilities. Of course, most of the molecules that we're dealing with don't have just hydrocarbons, don't have just carbon or hydrogen. So what is the effect of introducing heteroatoms? Here is butane, C4H10. Yeah. Let's add an OH group. Let's add an alcohol on the secondary carbon. And let's look at the impact of incorporating that heteroatom on the double bond equivalents. Notice that when we add an OH group, when we add an oxygen without adding any pi bonds or rings, the number of hydrogens doesn't change. Oxygen in a saturated context can be bonded to two different things. So it's like we just inserted an oxygen between this carbon and that hydrogen. It never left. So we can ignore the number of the number of oxygens when calculating double bond equivalents. Also, same thing for sulfur. In other words, if we did the math here, double bond equivalence for this molecule is 0, even though it's got an oxygen. So you can totally ignore oxygen when calculating double bond equivalents. Yeah?
Does it know that oxygen is double bonded to?
Well, the formula would take care of that even without accounting for the oxygen. So C358, C4H8O for that molecule, that would have one double bond equivalent. We didn't have to add or subtract numbers of oxygens, we just ignored it, and we'd still get the right answer. Yeah. Now it's a little different if you add nitrogens. So again, let's compare what we're going to draw to the saturated hydrocarbon butane. Let's put an amino group instead on that secondary carbon. And notice what we did when we inserted the amino group in between that hydrogen. We added another hydrogen because nitrogen can be bonded to three things, not just two. But we didn't introduce any double bonds. The formula here is C4H9N. Now, if you didn't account for the number of nitrogens and you tried to do double bond equivalents, 2 times 4 is 8 plus 2 is 10 minus 9 is 1 divided by 2. Half a double bond equivalent makes no sense. You can't have half of a pi bond or half of a ring. Yeah? Were there? Thanks. Sorry. I struggle to do math, among other things. 3, 6, 8, 9, 10, 11. Yes, thank you for that. Let me try that again. If we tried to calculate this the normal way, 2 times 4 is 8 plus 2 is 10 minus 11, negative double bond equivalence, negative half integral double bond equivalence makes no sense at all. You can't have negative double bond equivalence, and you also can't have half integer values. So what we need to do is adjust our formula. For nitrogen-containing compounds, double bond equivalence is 2 times the number of carbons plus 2 plus the number of nitrogens, because every nitrogen we introduce without introducing a double bond or a ring comes with its own extra hydrogen. And then we can subtract the number of hydrogens and divide by 2. Similarly, if we add a halogen, a halide, and look at that formula, this is where I got mixed up. The halide decreases the number of hydrogens by 1, because a halide can only be bonded to one thing. So when we replace the purple hydrogen with the halide, there's no other hydrogen hanging out on that halide. If we did the math here, we would, without accounting for this, we'd come up with double bond equivalence equals 1/2, which is silly. So what we're going to do is adjust the formula, and we're going to subtract the number of halides, where X equals chlorine, fluorine, bromine, iodide, minus the number of hydrogens divided by 2. So those are formula you can look up, of a useful thing that you can write down in your notes and make sure you've got. You don't need to memorize it. But this is very useful in figuring out what your options are in an NMR structure. Okay, questions about that? Is nitrogen supposed to be in that equation? Yeah, this is an equation you can use no matter what the formula is. If there aren't any nitrogens, you just ignore the N, right? Put 0 in for there. If there's no halides, put 0 in for there. Okay, so let's practice with this particular example. Let's start out with this formula, C4H8O2. Okay, real quick, just figure out how many double bond equivalents, if any, you see there. Is it 0? Is it 1? Is it 2? Just do some arithmetic. If you're like me, you write it down on paper, because my brain is notoriously unreliable when it comes to addition and subtraction and adding and subtracting. See, I said it twice. Dividing, multiplying. Common sense is also a weakness of mine. But. Okay, how many double bond equivalents do you see? Just one, right? One pi bond or ring. All right, that tells us something about what the molecule is going to look like. It narrows our possibilities. Next, we're given IR information. And in the IR, you're basically looking for peaks that correspond to important functional groups. The two excuse me, that are most useful are a peak corresponding to a carbonyl group, which tends to be in the 1600 to 1800 inverse centimeter region, or an OH group, which tends to be in the 3000 to 3500. The carbonyl peaks are sharp and strong. The OH peaks are broad and strong. Strong means deep, low percent transmittance, large absorbance. You can look up in the text for examples of this. The fact that we see a strong peak at 1700 wave number is consistent with the presence of a carbonyl group. That takes care of our one pi bond or ring. So we've already found data that are consistent with the molecular formula. And you're going to see in general with NMR, you'll have more than enough information to solve the structure, and you will see different pieces of information telling you the same things, and that will confirm that what you're drawing is correct. All right, so let's now look at the peaks. I like to start, and you don't have to do it this way, but I often tabulate the information I'm obtaining from the NMR spectrum in a table format. On the third column, I usually put something having to do with peak splitting, that is, how many protons are adjacent. On the first, I put chemical shift. In the middle is something that is called integrated peak area. And this is something I haven't told you about yet. But you may have learned in calculus how to calculate the area under a peak. If you want, you can divide that into little parallelograms and add them all up once you calculate the areas. Or if you can come up with a function that describes the peak, you can integrate it over a certain region. The area underneath a peak in the NMR is related to the number of protons represented by that peak. And the computer will do this for you. You just have to tell the computer when to start counting and when to stop counting. And then it's going to measure and draw a line over your peak and write a number by that line. That number, you could actually measure from the top of the line to the bottom with a ruler and you'd get a number, but it's going to give you a number for that line in arbitrary peak area units. Could be a decimal, could be an integer, you just never know. Let's suppose that the number was 48 here. Now, by itself, we have no idea whether 48 integrated peak area units means 1 proton, 2 protons, 3 protons, 4, or more. But when we start comparing that peak to other peaks, we can get an idea. So let's suppose we were told this peak integrates for 72 integrated peak area units, arbitrary peak area units. Now we can start to explore the relationship between these two peaks. We can consider ratios between the two that are consistent with different numbers of protons. For example, is it a 1-to-1 ratio? Well, clearly not, right? Is it a 1-to-2 ratio? Smaller peak is 1, larger is 2. Well, not quite. 48 times 2 is 96, so you're off by quite a lot. 1-to-3, well, certainly not. So let's try 2-to-3. Yeah, I mean, if you divide by 24, then this becomes 2 and this becomes 3. So that's okay. I chose the numbers deliberately. Notice you can't tell the difference between 2-to-3 and 4-to-6. It's just about the ratio, and you have to use other clues to determine what it's going to be. The other thing is that these numbers are rarely this accurate. Often you're looking for ratios where the numbers aren't going to be perfect. So as an example, in the data that we have here, you have 3 peaks. One is 23 integrated peak area units, the other's 29, and the other's 30. With experience, you can look at that and say, that's basically a 2-to-3 ratio. But I find students are sometimes uncertain about this. Couple of ways you can do this. First, if you want to, and you can add up all of the integrated peak area units. And then you can divide them by the number of protons that are in your molecule, in this case 8. You'd come up with something like 10.2 whatever, 10.25 maybe. And then you go and divide each of these by 10.25 and you come up with some number. Now, the number you'd come up with here is going to be bigger than 2.1 or something like that. Who knows? I don't know. But it's not going to be 2 exactly. So does that mean you have 2.248 protons? No, you can't have non-integer numbers of protons in a molecule. They come in discrete units, right? So the best you can do is say, okay, 2. Similarly, 29 divided by 10.25 isn't quite 3, but it's close, and that'll be close enough. So alternatively, if you don't want to take this approach where you add things up and then divide each of these peaks by a number that represents 10 peak area units per proton, instead just round down or up as appropriate. 20, 30, 30, then it becomes clear. You're really only looking for one significant figure of information here. All right? So in terms of integrated peak area, for the peak at 4 ppm, we'd say that probably represents 2 protons, or it could be 4. For the peak at, let's see, 2 ppm, that represents 3 protons. For the peak at 1 ppm, that represents 3 protons. It might also represent 4 to 6 to 6, but we know how many protons we have. And so the only way to end up with 8 protons while keeping these ratios is to have them be 2, 3, 3, because that sums to 8 conveniently here. All right, let's look at splitting. The peak at 4 ppm is a quartet. I'm going to abbreviate that with the letter Q. This means it is likely next to 3 protons, probably a methyl group. And we'll call, for the sake of our discussion, we'll call this peak A. Peak B at 2 ppm is a singlet. We'll abbreviate that with an S. That means it is next to 0 protons. And then the peak at 1 ppm, peak C, is a triplet, which means it is next to 2 protons, and most likely that thing that it's next to is a CH2 group. All right, and I did it again, sorry. Let's summarize what we know and sort of list the fragments of this molecule that we can account for. So in the IR, we had a carbon double bonded to an oxygen. In the NMR, we have A, which looks like it integrates for 2 protons. So that looks like a CH2 group next to a CH3 group, and only a CH3 group. In other words, there's no protons on the other side, because a CH2 group can be bonded to 2 things. B looks like a CH3 group next to no protons, and C looks like a CH3 group next to a CH2 group only. All right, what do you see with peaks A and C? Does a structure come to mind that would account for both of those peaks? So CH3 next to a CH2. Now, this would be A and this would be B. What does the peak for A tell you about what can be here? Can it be a proton? Can it be anything that are protons? Like, could it be in the other methyl group? Right, because otherwise, if it were adjacent to 6 protons, that would be a different kind of pattern. So yeah, A and C together are consistent with an ethyl group. And let's examine that again. C in this structure is a methyl group adjacent to 2 protons. That should be a triplet, and it is. A is a quartet. And it integrates for 2 protons, so it should be a CH2 group adjacent to only a CH3 group. There, whatever is here, there can't be any protons on it.
So that's the carbonyl, and then there's the methyl.
So it could be a carbonyl, exactly, because you have something there. The other piece we haven't accounted for is the other oxygen from our molecular formula. So we have to think about that too. And then for peak B, yeah, you have a methyl group, and whatever is over here, there are no protons. So what we're going to do now is just start spitballing possibilities, and except not spit because of COVID. So we're going to start crumpling up paper and throwing out, I don't know, possibilities. And sometimes students are reluctant to do that because they feel like if I write it down on paper, I've committed to it, and what if I'm wrong? So what if you're wrong? Look at the data, compare the data with your answer, and think critically about it. And if you draw something wrong, you should be able to convince yourself that it's wrong based on the data. This is what scientists do, come up with a hypothesis and see whether it agrees with the data. So the pieces I have so far are ethyl group, methyl group, carbonyl, and oxygen. So I can stitch those together, I think, in two possible ways. I could have the methyl group adjacent to the oxygen, then put the carbonyl here, and then put the ethyl group here. The other possibility would be to put the carbonyl here, the oxygen here, and then the ethyl group here. Can anybody think of any other possibilities that account for this splitting pattern? Some of you might say, well, why not just put the CH2 group here by the oxygen and then the carbonyl in between those two? But that would destroy the splitting pattern that we've identified for the ethyl group. All right, let's look at those possibilities and let's see what we can find. When you have two possibilities that both agree with the splitting pattern, you want to go back to chemical shift to distinguish between the two. And in this molecule, the thing that is likely to have the biggest effect on chemical shift is that oxygen. Recall, and you can look at this in your chemical shift table, but being adjacent to an oxygen generally causes you to have a chemical shift in the 3 to 4 ppm area, whereas being adjacent to a carbonyl generally puts you in the 1.5 to 2 ppm region. All right, so for option number 1, let's predict what we would see for this methyl group adjacent to the alcohol, or adjacent to the oxygen. We would predict a chemical shift in the 3 to 4 ppm area. What do we observe for that methyl group? I mean, we would predict that it's a singlet. So for the peak that corresponds to the singlet methyl group, that's peak B, do we observe a chemical shift consistent with this hypothesis? No, in fact, we observe sort of 2 ppm. So the option 1 is inconsistent with the data. All it took was one comparison. I had to make the right comparison. If I had started with this methyl group, CH3 adjacent to a CH2, or the CH3 is at the end of a chain, it should be a triplet. Well, that's actually true for both of them. So you got to look for the differences between the structures and then see whether the data agree. Let's now look at option 2, which has the CH2 group adjacent to the oxygen. We're going to predict a chemical shift of 3 to 4 ppm based on the table. And based on the structure, we would expect this to be a triplet. We actually observe for peak A, a chemical shift of 4 ppm that's a quartet. I'm sorry, I got confused. For CH2 that's adjacent to a CH3 group, we predict the splitting to be a quartet. I spoke incorrectly. It's adjacent to 3 protons, so it should be a quartet. That's exactly what we observe for peak A. It's a 2-proton quartet that's at 4 ppm. So structure 2 has got to be it. Now we can go back and look at the other 2 groups in this molecule to just confirm that they are also consistent with the data. A methyl group at the end of a hydrocarbon chain, not adjacent to an electronegative atom, but adjacent to 2 other protons. I expect a triplet integrating for 3 protons, and I expect it to be at fairly low chemical shift. That's what I observe. Proton C. We've already gone through proton A. A methyl group adjacent to a carbonyl, I predict chemical shift should be in the 1.5 to 2 ppm region. I also predict, since it's not adjacent to any protons, it would be a singlet. That is indeed what I observe for proton B. So some people think they're done when they draw a structure. When you draw a structure, you've just hypothesized what you think the data are. You're not done until you compare your structure with the data and confirm that they match. Okay? This is science. This is not throwing darts. We're not just throwing something to see if it sticks. We're comparing our hypothesis with the data. All right. Questions so far? Yeah.
How did you know that there was going to be a double bonded oxygen and then an oxygen?
Okay. Yeah, Staten, the question's good. How did I know that the carbonyl and the oxygen were going to be attached together instead of separate? The reason I knew that is because there's simply no other way to draw it. I suppose we could have drawn this option where we spaced things out. But if that were true, we would predict singlets in each of those cases, which is not what we observe. Now, spoiler alert, problem F actually is this structure. We won't go through it, and you can go through it on your practice exam, but for problem F, you see 3 singlets in a 2 to 3 to 3 ratio. And you also see a peak at 1700 wave number in the IR. Same molecular formula as before, only with the same number of double bond equivalents. The only structure that matches that is this alternative. All right. So you're looking for evidence that your proposed structure matches the data. The absence of an observation can be just as informative as observing something else. The fact that these peaks in problem F are singlets and not split is crucial information that allows you to solve the structure unambiguously. All right, other questions? Yeah?
Maybe not for like right now, but maybe for next time, is there any way you could write like a list of like the steps, like peaks that calculate level one equivalent?
A flow chart of how to sort of work through these problems. Yeah, we could talk through that. And actually, there's no right way to do this as long as you're considering all the data. So, I suggest you find a process that works for you. And there are tons of these problems in the practice exam. Actually, these problems are from the practice exam. So it's useful to get started and wrestle with some of these, and you'll come up with your own approach. But I can sort of summarize that. Someone from the chat is asking, where is the table where you can look up the strong peaks? Is there a link on Learning Suite? It's in the book in chapter 13 for the IR peaks. The ones you want to remember are the carbonyl peak and the OH peak. I don't have a page number, but presumably you can find it because you have access to the text. So you're on your own there. Sorry. Sometimes my children ask me to do things that I prefer that they do for themselves, and sometimes they complain. Adam in particular has been complaining lately about having to shower and brush his teeth.
How old is he again?
He's 10, so the shower, we're just, maybe he can go a few days without a shower, but teeth brushing, I mean, man, that's just nasty to not do that. And every night we have this argument, and he often explains why he shouldn't have to, and I tell him, guess how much I care? And the answer is zero. I care 0 caring units, or 0 much, depending on how I'm feeling. So look that up in the text, and there's a similar figure. I don't know which figure it is, but if you go to chapter 14 and you read through the NMR chapter, there's both a figure and a table that summarizes the chemical shift information. You're welcome to screenshot that or write it down, have it all in one place. That's fine, but you should have access to that. Any other questions? Yeah.
Will we always be able to identify one correct structure, or might we ever have a couple of possibilities?
Will you always be able to identify one correct structure, or might there sometimes be possibilities that equally account for the structure? No, In the problems I'm going to give you, there will be only one answer that is consistent with all the data. And frankly, that makes these problems a little bit easier when it comes to multiple choice, because you can look at all the options and you're like, no, that one's not going to work, if you know how to think through this. Yeah, so there'll always be one answer. That's not to say that there aren't molecules that would be difficult to distinguish by NMR. I'm certain that they are, but for the problems I'll give you, there'll be a way to get the correct answer. Okay, other questions? Let's get started on another. We won't have time to complete it, but it'll be useful. So for a molecular formula C8, H11N, go ahead and figure out how many pi bonds or rings you got to have in that thing. And these problems are actually in that practice exam 4, so you can, they're pasted in there exactly like this, so you'll have access to this offline. But go ahead and do the arithmetic, paying attention to the nitrogen. I think in the winter 2020 semester, before all hell broke loose with COVID, and there were tons of students in the class, I would ask a question and then I'd play the theme song from Jeopardy while they wrote the answers. And some of them were entertained, but by far the majority of the class said that upped their anxiety to unacceptable levels. So we won't do that here. Anybody got an answer? How many double bond equivalents do you see? 4? Okay, that's correct. There are 4 pi bonds or rings. Now let me tell you a secret. In a molecule that's fairly small, there's not that many ways to get 4 pi bonds or rings. And in fact, when you observe 4 double bond equivalents, you should right away be thinking about the possibility of a benzene ring being part of the structure, because a benzene ring accounts for all 4 double bond equivalents in a very small number of carbons. So that's just a rule of thumb. It doesn't always have to be that way, especially if the molecule's bigger, but in a molecule of this size, and no, I don't have a limit to when this rule of thumb goes away. If you've got 4 double bond equivalents or more, you should be considering a benzene ring without knowing anything else about the molecule. Then in the IR, there's a bunch of peaks, which we're not given any information about how sharp or broad they are. This is distracting. This is just distracting information meant to overwhelm you. So sidestep it and ignore it, because probably there's enough information elsewhere, right? So I'm just going to ignore all of this because there's nothing clear about what the peaks should be. It turns out these numbers here are consistent with amino groups and H bond stretches, but you don't have to know that to get this question right. Well, I'll show you that in a second. All right, let's start looking at the chemical shift and the kinds of peaks. Fortunately here, they've made it easy for you because they've figured out what the proton ratios are from peak to peak and already concluded how many protons each peak represents. And notice that this adds up to 11. Here in the region from 7 to 7.5, we see some messy peaks, sort of 2 sets of messy peaks, and you're told they integrate for 5 protons. Now, when you see a set of messy peaks like this, you should be, and especially if it integrates for more than 1 proton, you should be thinking, I may not be able to interpret the splitting pattern there. It might be too complicated. Splitting patterns can be complicated when 2 peaks have very similar chemical shift and they're coupled with each other. There's some weird physics things that happen when that's true, and the peaks get messy and you can't analyze them in the way that I've taught you. So all you would know from this set of peaks is they're in the region that's consistent with being bonded to a benzene ring, and there's 5 of them. Fortunately, go ahead.
How do we know that there are 4
The ring has 3 double bonds, but the ring counts as a double bond equivalent as well. Yep. Fortunately, you're told that these are protons that are in a region attached to benzene ring, and there's 5 of them. The only thing that can be, even if you don't know what the splitting pattern there tells you, is a mono-substituted benzene ring. That's it. That's all it can possibly be. All right, we'll have to leave it there and pick up there next time. So have a good couple of days. Next time is our last OChem lecture. So prepare yourselves emotionally for a gut-wrenching goodbye.